Before we start solving a problem, it's important to review some of the basic rules to prepare and form Lewis structures. This slide refers to the octet rule exceptions. We can think about three types of exceptions. The first one refers to when we have electron deficient atoms such as boron and beryllium. As we can see in this example, beryllium chloride has beryllium as the center atom, and this atom does not have an octet rule. We have simply two single bonds, that is 4 electrons. Another example of electron deficient is boron trifluoride, in which boron is the central atom. Here we have only 6 electrons defined by each of the single bonds. The other type of octet rule exceptions refers to free radicals, in which we have an odd number of electrons, which makes it impossible to have 8 electrons surrounding an atom. In this example, the octet rule is violated in regards to the nitrogen, the central atom, that has 3 single bonds, that is 6 electrons, and 1 electron, lone electron, so that's 7 electrons. And this one has a resonance structure in which the lone electron is localized in oxygen. In this situation, the oxygen does not meet the octet rule. We have 1 bond, and then we have 2 lone pairs, so that's 6 electrons, and 1 single electron, that's 7 electrons. The third type of exception to the octet rule is for nonmetals from period 3 or higher that have an expanded valence shell. And this is possible because there are available d orbitals that participate in bonding. 2 examples that we have here is phosphorus pentachloride, in which the central atom phosphorus has 5 bonds, that is 10 electrons, 2 more than the octet rule allows for. The other example is sulfuric acid, H2SO4. The central atom of interest here is sulfur. This has also an expanded valence shell. We can see that it has 1, 2, 3, 4, 5, 6, that is 12 electron pairs. Indeed, this is higher than the octet rule allows for. So now, with this background, let's move on to solve a problem in which this concept needs to be applied. The problem reads, there are 3 species below, and they do not obey the octet rule. Draw a Lewis structure for each of these structures and state the octet rule exception. So take a few minutes to think about this problem, propose a solution, work the solution, and after that let's compare our answers. The plan to solve this problem will consist of first counting the valence, bonding and non-bonding electrons of each of these structures, draw the corresponding Lewis structures, and finally identify the atoms in which the octet rule is not met. Let's begin with O3-. So O3- can be represented as 3 oxygens that are connected by a single bond. It has 3 times 6 electrons plus 1 corresponding to the negative charge. We have 19 electrons. Bonding electrons, we have 2 bonds times 2 electrons per bond, that's 4. Non-bonding, we have 15 electrons, 19 minus 4. So we are going to place 6 electrons on the first oxygen, 4 electrons on the next one, so that's 10, and we have 5 left to be placed on the last oxygen. The exception here is a radical because we have a single electron not meeting the octet rule. It's important to mention that because this structure has a negative charge, we need to place the entire structure in brackets indicating the negative charge. There is also the possibility of having resonance structures in which The oxygen that has the single electron is a different one. So for instance, we can imagine that we take the electron from this oxygen and pass it to the last oxygen, and then if we place again electrons, this would be the oxygen atom that has now the radical properties. We can write a last resonance structure in which the first oxygen is the one that lacks the complete octet rule. So that means that we will have then a lone electron on the first oxygen, 4 electrons on the second oxygen, and 6 electrons on the last oxygen. Let's do now the following structure, the next structure, XeF2. The central atom here will be xenon. So we are going to use a bond towards the fluorine, towards each of the fluorines. And then let's count the number of electrons that we have here. So valence electrons, we're going to have 2 fluorine atoms, 7 electrons each, plus 8 electrons for xenon. We have 22 electrons to place. Bonding electrons will be 2 bonds times 2, that's 4 electrons. The non-bonding electrons will be 22 minus 4, that's 18 electrons. So let's begin by placing the electrons then on fluorine first. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And then we have 6 more that will be placed on xenon. And as we can see, xenon has an expanded shell way above the octet rule. Let's work on the third structure. BeF2. Central atom is beryllium, and we have 2 fluorine atoms connected to beryllium. Valence electrons, we have 2 times 7 for each fluorine, plus 2 electrons for beryllium, that's 16 electrons. Bonding, we have 2 times 2, 4 electrons. Non-bonding, we have 16 minus 4, 12 electrons. Let's place those electrons, starting with the most electronegative atom, or atoms. We place 6 electrons on each fluorine atom, so that's 12. There are no electrons left for beryllium, so the exception here is going to be because of beryllium, which has an electron deficient configuration.